Hello everybody, this is Peter Baumann speaking. It's my pleasure to be here as keynote speaker of SSDBM. Although it's a virtual one, I hope you're all doing fine in these difficult times. I would like to tell you about the research that has brought multidimensional arrays or data cubes into database research after quite some journey. And that actually is coming from, as you can see here, a place that is Jacobs University in Germany, where I'm leading the large-scale scientific information systems research group, where we are dealing with raster services, well, whatever you want to call it, arrays, rasters, gridded data. In the end, it all boils out the same pretty much. Here's a link to our research group, and we have a spin-off company for giving that kind of support to the software that a university cannot do. And that actually is the Rasterman system for Raster Data Manager, which has pioneered array database systems. Aside from that, we are also very actively engaged in standardization of such data cubes. And by the way, a bit of advertisement: if you want to come to us for a studying or for a research visit, we are all English campus. We have about 1,400 students of about 110 plus nations, so everything down to administration is really in English language. No need to learn German. Okay, end of advertisement. What do we want to talk about today? I want to first motivate array services because it's still not entirely mainstream. Talk about how to do modeling of arrays on a conceptual level in a database system, and then move over to architectures, applications, and then it's time to wrap up. So, how do I motivate the use of data cubes or arrays to people that should use that can make use of it? Actually, when I talk to earth scientists or large-scale data centers, they typically have some homegrown method of maintaining array data, and that typically is just a bunch of files. So we are back with good old file-based data management, and we talk about large numbers of files, millions of them. This effectively prevents large use, and so I'm telling them, what if you wouldn't have to find the appropriate file here in some format which is maybe not your favorite, but if you could move freely in space. That is what you can do with Google Maps too, but also in time. And by the way, in all spatial dimensions, also in elevation or in bathymetry down into the sea. So you don't talk about file boundaries any longer, you just have pixels and you move freely, and you can do that in multiple dimensions, through 1, 2, 3, 4, 5 dimensions in the same method. Okay, that's one of the advantages. We would call it data independence and information integration. So, where does that occur? Actually, the answer is pretty much anywhere. These resemble, technically speaking, in our experience, sensor data, image time series, model output like weather forecasts, or general statistical data. I have collected a couple of application fields here where you find life, earth and space sciences, but also engineering, and of course management controlling when we talk about OLAP data warehousing, and also fintech and the like. So really almost everywhere, although with a different twist, with a different kind of look and feel and handling. So why would I want to serve them out? Excuse me. So why not just file download and I do everything on my desktop? Well, let me show an example. The normalized difference vegetation index, or NDVI, is a well-known formula to find out whether some pixel contains vegetation or not. You see an example here that is a so-called false color image, where you have infrared, red and green bands. This is why it looks so funny. But actually you can see trees there, small red dots. That is vegetation. And now you can compute the vegetation index, which is actually a well-known formula, and you can do a threshold to see how much likelihood of vegetation is there. This is processing. Okay, we could do that at home on our desktop, of course, but the one thing is we don't want that. We want to see a result, we want to see an answer. But here's more to it. let me jump over to some website that we have built for demonstrating Datacube standards and show you a particular demo that actually shows those both images in arrays. So now we see a race going on. On the left hand side, the image is served as a file. So Apache takes the file and serves it out to this client. On the right hand side, we have imported the same image into an array database system, and then we compute the NDVI and get the result. Now on top of the images you can see how long it took. Isn't it amazing? The right hand side should be slower, but it is faster. Well, let's see. The processing actually is so fast that we don't realize it. But there is something else. Look at the pixels there. On the left hand side, from server to client, we have to deliver 24 bit per pixels. On the right hand side, we transport 1 bit per pixel. And actually, if you look at the image, that compresses really nicely. So bottom line, on the right hand side we transfer kilobytes of data, on the left hand side we transfer megabytes of data. So the difference is in the amount of data here in this example, and that is something that we commonly observe. The more exactly you can tell the server what you want, the more exactly you can get your result delivered. I changed the threshold value here so that we run the whole thing again, and you see the differences. Actually, this is public, you can invoke it and run it yourself. So actually the high level service is faster, and that is performance plus also quality of service. I don't get a task, I get an answer. So coming back, it's really worth being able to do such kind of things in the server. That, by the way, is the corresponding query. Okay, so arrays and their processing, we like to call that actionable arrays, is something that makes sense. We want to have services, and large services are being built actually in many different areas. I have collected areas randomly here. This is just a random accumulation of some areas where you find that underneath, from a database modeling perspective, you just find a few data structures actually. So if we abstract that away, we find just a few structures that can be characterized as sets. This is where we have relational models, hierarchies. Database support is available, for example, through XQuery. Graphs as an exciting research area with languages like Cypher and Neo4j systems. And then we have arrays as a fundamentally different data category. Now you can try to emulate, of course we can try to emulate hierarchies in sets, for example, but we know about the shortcomings. Same with graphs and same with arrays. It has been tried and it has been demonstrated that it does not really work out satisfactorily. Some special niches have still found commercial success, in particular OLAP with very sparse data cubes, but not in general. Interestingly, as we talk about the title From Underdogs to First Class Citizens, the Underdog experience I had actually way back 1996 at SSDBM, when I first presented the rough idea of what should become array databases later on. Then I had to hear from some well-respected colleague, that won't work, and if it will work, nobody will use it. Okay, so much about the encouragement, and we moved on and indeed did it, and I will show you today that it is being used. So what do we want? Let's step back a little bit and do an abstraction as the developer of some new kind of database system. We want to work on arrays and we want to analyze them. I like to define it this way, that array analytics is the efficient analysis on multidimensional arrays of a size orders of magnitude above the evaluation engine's main memory. So we talk about the server as the evaluation engine, and you finally say, wait a moment, I have an engine with 128 terabytes of RAM. Then I tell you, yes, and the European Center for Medium Range Weather Forecast has more than 200 petabytes of data cubes. So whatever you come with, I will find arrays that are larger that don't fit into RAM. And this is obviously where it gets interesting. The essential property of arrays that differentiates them from others is the n-dimensional Euclidean neighborhood. So, in other words, whenever I access the red pixel somewhere in an image or an image time series, it's extremely likely that in the next moment I will want to access the blue neighbors as well. So this is what needs to be supported efficiently. Okay, as per operations, in the end, such arrays are vectors or matrices or tensors in the general case, and the operations naturally are linear algebra. So array analytics is all about tensors and linear algebra plus a little bit more. Okay, so this is what we want to do, and we have set out to do this actually at some time when databases were very much focused on tables. And I remember a talk where somebody kept on yelling, "This is not SQL." Today I would say, yes, sure, it's no SQL. So arrays was started, and there were some attempts which unfortunately were discontinued. It was some thesis work, and when the student left, everything was abandoned, unfortunately. But then actually gradually some wave came up, and many of you will likely know SciDB, which is just one proponent, one epicon that came up, and there are many more today actually. So that has grown into a fully fledged research field, fortunately. Here's an example of what we did at some time way back, actually with a German remote sensing data center. So that is a satellite image built up of about 10,000 individual scenes, as they call it, so images. And the whole thing is three-dimensional. Actually, it has a time component, so it's x, y, and time. The web interface was not exactly what you would expect today, so it was way back the simple ways that HTML offered. But you see already that we could extract a three-dimensional time cutout from a three-dimensional data cube, and actually we could also get some images out, time slices, diagrams, time series, etc. So things that you want to do as the basics, that is extraction of data. But look at the year, that was back in 2002 actually, when we did this as likely the first Datacube service that went online. Of course today everybody knows how to do that better with in particular better client functionality. So what's around? Array services are nothing new. In weather forecast, supercomputers work on arrays for a long time, but they don't serve it. So if you look at services, we find, for example, array databases that stand out through their declarative and optimizable query languages. There we have Rasterman, we have Cycle, SciDB, we have something like Postgres Raster, which is focused on a particular application domain, Teradata, Extasit, and many others. They distinguish actually in that some of them say see arrays as a table. So actually you say create array quite the same way as you say create table in a database system. That can become a little bit weird when users should be allowed to create arrays on the fly, many of them, thousands of them, and then they need to have schema management capabilities and rights, which is maybe not exactly what the administrator wants. But there are further difficulties as well, like for example doing combinations, so joins of them. Another approach is to see such an array as an attribute, pretty much like a blob, just with a multidimensional structure, and this is actually what most approaches today follow like. Aside from databases, you find MapReduce based software with their specialized parallelization paradigm. They have a Java and Scale API or Scalar, which means programming effort, so it's for experts only. And then people have built specific array layers on top of the generic MapReduce style paradigms, and so you find Sci Hadoop for science data, Sci Spark, GeoTrellis, Mr. Geo, Calvalus, and further ones. With a Sci, you see that actually the history is from scientific data, but as I try to motivate, of course, arrays are by far not limited to science only. Then of course you find libraries and command line tools, as I said, with a long tradition in high performance computing. So this is not yet a service, you have to wrap something around it. And there you find OpenDAP as a prominent tool that was built to conveniently read and evaluate netcdf files. Excuse me. And many more of them, such as, for example, Python libraries that are pretty well known these days, like Xarray. And then libraries also means mentioning TileDB, for example. Google Earth Engine is another one. I found it unclassifiable, doesn't fit into the schema. It's a bespoke application, which actually is not truly multidimensional. It's 2D plus extensions into 3D, so it does not entirely fit into that schema. If you want to read more about that, there is a Research Data Alliance report from 2018 that compares 19 different systems, so you can look at functionalities, and there are also some benchmarks in there. Okay, a big question that again and again reached me is, why don't we just implement that as an object-relational extension? Actually, you find systems doing that. Postgres raster, for example, or Teradata arrays. Problem: an array is not a data type. It's a type constructor. Just like stack, for example. Stack is not a data type. You can make it a data type by instantiating it, like a stack of integers, a stack of floats, etc. Same with arrays. Arrays are parameterized with the dimensions and the extents, and by the way, with the cell type. And object-relational extensions allow to do user-defined data types, but not type constructors, and that means you have limited opportunities. So the Barrodale grid data blade, for example, defined arrays as 5-dimensional by default, so they fix the dimensions, and then you can say, but I want to only have some let's say subset of dimensions, so restricted to 2 dimensions, restricted to 3 dimensions, so. And also the provisioning of operators is conceptually difficult here. In the end, actually, turns out that you need to implement the whole stack if you want really good array support, and that, of course, is a hell of a lot of work. If we have done that, I can tell you it is. So how should we model arrays in the first place? Let's not jump into implementation right away. We looked, when we built an algebraic framework to conceptually describe arrays and array services, into several domains. For example, there was the ISO computer graphics reference model. Visualization also had a reference model. Image processing languages were an interesting field of study. And what I liked in particular was AFATL image algebra, because, as the name says it, hey, it's formulated in algebra. That's good for database guys. So that was helpful in understanding operations and also translating that later on into a specific database suitable algebra. So AFATL image algebra I would consider as the main source of insight into image and array operations. Good. Here are some design decisions that have been made early on. One thing is, we want to capture the complete semantics in this algebra. Some systems like RAM and SciDB do it the following way. When it comes to operations on array cells, we notice, we apply the same operation on all the array cells simultaneously, and that is a nice pattern. This pattern we capture with an apply function. So apply gets an array as input, and it gets a function that is to be executed. You realize already, actually apply is a second order function. This second order function, however, does not know much about the array operation to be executed. For example, you can do those things only which some people call embarrassingly parallel, but you cannot do stuff like convolutions, for example. So the design decision was that in array algebra, when we built it, all operations should be formalized. Apply is a black box, by the way, also for the optimizer. We wanted to have everything explicit. The next thing is, which way should this processing work? Should they work in the way that I look at the result and go to the origins to find out what pixels I need? Or should I start from the origin pixels and say, okay, and how do they affect a result pixel? that makes the design fundamentally different. We decided that we want to be declarative, we want to describe the result, and so actually the array expressions that you're going to see later actually describe the results, and how the evaluation is done is very much left to the engine. Then we have another idea. Now, it was very clear early on, if we just build something for arrays only, then we have another silo for another data structure, and that is not going to fly, because everybody has extra data, metadata, as scientists like to call it, that describe those. Okay, so we actually need to have a way to connect to well-known data models, and at that time there was only one, and that was SQL. Okay, so how should we integrate that into SQL? Change SQL? No, nobody would do that. So we went for a two-step approach. First, define a freestanding array algebra, and then think about embedding that into SQL in a minimally invasive manner. So, this algebra actually turned out to be nicely minimal, and it turned out that we can use that not only for designing our language, but also for defining the storage mapping and for expressing optimization. It consists of only two basic operations, the array constructor and a condenser, which I will show in a minute. We put much emphasis on having implicit iteration there. Iteration is intrinsic to arrays. Of course, you always iterate, but we don't want to have explicit loops, and by avoiding that we obtain a declarative and safe language. And then finally, the array query language is simply SQL with embedded array expressions. Of course, forbidding explicit loops also limits expressiveness. That was tentative. So the question is, how far can we go? Well, we can go up to something like, for example, discrete Fourier transform. We can do convolution kernels, etc. We cannot do, for example, matrix inversion, because that is an intrinsically iterative process. And it's one of our current research thrusts to see how far can we extend the language to have loops but still remain declarative and safe. But back when we started with that, the first operator was to have a constructor that generates a new array and initializes all array cells with some value. Here's a very simple example that shows this M-array operator, how we write it in ASCII, which is sort of easier in my PowerPoint. We create an array with 2 dimensions. The axes are x and y, and the extents in both are 100 steps. So 100 by 100 matrix, and the values actually are given in that case by just adding up the coordinates. So you would add some gray bar image in this case. But you can write anything in the values clause. You can, for example, clone from another array, you can combine arrays, etc. This general principle that actually led to many specialized shorthands, subsetting, for example, the good old bracket notation where you want to have a cutout in the first dimension, in the second, and in the third dimension. That is simply a special case of the M-array operator. We also implemented them as a special case because these special cases lend themselves well to specialized optimizations, to optimize code in the server. So we have, in classical notation, a different access method that is particularly fast. And it has led to a class of operations that array algebra and AF-ATL image algebra like to call induced operations. The idea behind is simple. For every operation that you have on the cell data type, like integer, you have the same operation on array level. So if you can do addition on integer, you can do addition of arrays, cell-wise. If you have, let us say, multiplication, if you have division, if you have log, or exponential functions, etc., all of that becomes automatically available also on the arrays. That is much simplifying query writing. And again, that can be supported by optimized code. And this is, by the way, the class of operations that can be supported by the apply functions. And with that, we are leaving that because the next thing is already hard for the apply function. So the next one is the condenser operation, We called it Condenser, although it does the same thing as an aggregation in SQL. But we wanted to be able to differentiate so that we know what we are talking about. So a Condenser summarizes algebraically expressed. We have operator that is parameterized with an operation, the circle, and an extent, and some variable, lowercase x is bound to the uppercase extent, and then we just take every point at every position. We maybe apply some expression e to it, evaluate that, and then we combine following this circle operation. The semantics is that x visits each coordinate in this coordinate space exactly once. In order for that to work, this operation needs to be a monoid, and then we can write something like condense plus, so add up over that area, x and y in 0 to 99. And the using clause then gives us what to sum up. In this case, it's just some array elements, and that is actually the same thing as you would say sum over a in that area. Meaning, again, we can do shorthands here, and you find the usual suspects. So we would do count, sum, average, and so on over array expressions, which can well be subsets. So you can indicate a particular area within a cell array to be summed up. And of course you can do that over space and time. We are multidimensional. These two operations together make up the full algebra, and all the operations that we are using in Rasterman actually can be traced back, can be expressed in these two operations or a combination thereof. So what you find, for example, is selecting data, so doing subsetting. This is the bracket notation again to extract part of it. Or you can do some processing, like I want to find out where there are some particular high green values in an image. You can use it for aggregating, and that again lends itself well to be a predicate in the where clause. So it's not just about processing the select part, but also filtering in the where part. And then we have something that is down to earth, okay, that indeed transcends these array operations. It's about encoding data in the particular format that you would like to have. So with Rasterman today, we have about 110 formats that we support, from PNG for a simple image vision and rendering in a browser to NetCDF for scientific analysis. Okay, here's an example of first steps, I'm cautiously saying, into linear algebra. There is a vast field, and a PhD student in my group is currently evaluating, exploring that area. Here's a very simple example where you use the M-array and the condense operator for doing matrix multiplication. So M-array defines a matrix. This is the ij in the mathematical formula, and the value on each such ij position in the array is given by an addition, where we actually iterate again with iteration variable k, and the elements are given by multiplying a ik with b kj. This is very similar to the mathematical formula, so the structure is very much the same, just translated into some ASCII notation. So that is something that we can formulate conveniently. Also, histograms, for example, can be done. We would use the count cells operator here to establish a one-dimensional array that contains the array buckets, and then we get the intensities from 0 to 255 for some 8-bit grayscale image, for example. In the DeepBrain project, we actually study the coupling of machine learning with ArrayDBMS on the basis of linear algebra operation. Okay, then of course there are people who don't like that so much, but I'm looking at time, and actually I believe I skipped that. Yes, we have some concept for user-defined functions, but it doesn't give us more insight actually. Let's rather go into architecture. So how do we store arrays? Well, we could store an array in a blob. Not ideal. You would do a linearization in a blob that is implementation dependent, and a nicely rectangular area as the axis in that top right array would get linearized on disk into line by line by line different areas. And that means the diskette has to jump from one area to the next, and that makes reading of such a cutout really slow. Let aside the fact that a 100 terabyte array is difficult to put on disk like that. Okay, what else can we do? Well, we could look into the single pixels, and we could store them together with their coordinate. So we have a set of pairs, xi, fi, where x is a coordinate, a multidimensional coordinate, and f is some value, whatever. Okay, what happens now if we want to recollect? Well, actually the costs are not position correlated, so regardless of where the pixels sit, you find them at a constant cost. Problem, this constant cost is pretty high. So this explicit handling of coordinates is also not optimal. In particular, if you have dense images. So if you have a value everywhere, like in an image where you have a pixel color everywhere, you don't want to materialize the coordinates. That is different when you have sparse data. When you have very sparse data, actually this way of storing them is an excellent compression technique. And that is actually the technique that OLAP databases, specifically roll-up databases, pursue. And they can do that because the space is sparse. And it works only once the space is sparse. Nobody would ever think of storing a satellite image by splitting them into single pixels and their coordinates in a database. Everybody knows that the performance would be prohibitive. Okay, so we have two bad cases. Can we find something that works? Well, we could try to have a combination of both. So a two-level approach where we first do on the upper level a partitioning. That is like our approach number 2. We partition into slots that we address by coordinate. We don't call them slots, we like to call them tiles. Some people like to call them chunks. Inside such a tile or chunk, actually we follow approach number 1. We just brute force linearize. But that is not a problem, because our unit of access now will be tiles. We always read a full tile anyway, so we can handle the situation well. And we can get the usual support, like multidimensional indexes do, to quickly determine the tile that we need to load. So actually this is a combination, and actually every system working with arrays does it like that. So this partitioning or tiling is the standard way of storing arrays. Now the question is, and how do we do that tiling? I mean, we can do it with equi-sized tiles or in any other way. Paolo Furtado has investigated on that, and in her thesis she has classified tiling into their degree of regularity. So left hand side totally regular, right hand side totally irregular, and anything in between. And she has cast handling of such tilings into strategies which we have then made available in the implementation as strategies for the administrator. So we have enhanced the insert statements with a tiling clause where you can specify a strategy like area of interest and the default tile size and a few more things like compression, for example. Okay, most systems only support some regular tiling, and I frequently get challenged by people saying, oh, we don't need that anyway. Irregular tiling doesn't get us anything. Well, not quite. At the bottom you see an image that is taken from OpenStreetMap, and that shows their tiling. Okay, it's on vectors, but they have the same problem. Downtown New York City, you want to be very fine-grained because we have many, many vectors there, whereas in the Southern Pacific we can have one big blue tile because there are not so many streets. So OpenStreetMap has done the same thing. They have done an irregular adaptive tiling, and actually Paula's analysis has resulted in huge performance gains that can be achieved that way. Okay, so much about storage. Now to processing. I mentioned that we kept a very clear distinction between sets and array trees. So you see the standard diagram in the middle that has the pipeline of reading tables, doing the cross product, filtering and function application. This we leave untouched. The only thing we add is some operator subtrees in function application, so the select part and in the where part, that are array specific. So we only fiddle with the element trees. That is our area. You can see that such a query where we want to say all cells of A must be less than the maximum of B plus C together. Something like that translates into a query tree that has array operators and in the end accesses the array attributes that are embedded in tables. So actually arrays appear something like second order attributes, and SQL as such doesn't need to get changed in any way. And it opens ways to do extensive optimization and to do evaluation based on tiles, meaning that we can read and evaluate tile by tile by tile, and that allows us to process arrays that are larger than main memory. Okay, here's an example for such an optimization. So query rewriting we have shamelessly stolen from standard relational databases. That allows us to find the most efficient phrasing for a given query by just applying some rules. We have about 150 such rules in the system currently. Here is an example for it. We want to compute the maximum of the cells in the array obtained by adding A plus B cell-wise. In the query tree on the left hand side we see exactly that situation as in the query, a maximum of the addition of A and B. Now our rule says, wait a moment, this is semantically equivalent to first applying the max operator individually and then doing the addition, with a difference that now this addition is just an addition between two scalar numbers, whereas the other operators require transport of arrays, so they are more expensive. So as you can see, by substituting the left hand side with a semantically equivalent right hand side, actually you save 1/3 of the processing effort, 1/3 of the hot stream of the high traffic tile stream. You can retranslate that into the query representation, and then you find out that of course that is equivalent to max cells of A plus max cells of B. Good. What's always exciting in databases is joins. Joins are nasty beasts in arrays as well, and we have quite some challenges there. In particular, that arises from the tiling. I mean, if two arrays are to be combined and they have the same tiling, then it's easy, no problem. But what if not? It could be that some partitions are just shifted, as the example on the right hand side shows, and of course the arrays can have different size and they can be heterogeneous in shape. There has been some research by SciDB into getting things aligned, but in the end we found out you just can't do it. In particular not in federations that we will consider later on, where two data centers have individual ideas about how to do tiling on their arrays. So we need to live with that. And of course we want to avoid that we have to read subarrays multiple times. So if you evaluate B1 in this scenario, you would need to read A1 and A2 and A3. Sure, but then you come to B3, and B3 again needs to read A3, and that is no fun. We want to avoid that duplicate read to make the join efficient. So, or in other words, to reduce it from quadratic complexity to something like n log n or even better. Let's see what we can do. We want to find the optimal partition loading sequence, and actually there is an approach that you can do using a bipartite graph traversal. So you have red graph nodes and blue graph nodes, each one representing a tile, and then you just want to find a traversal path from one tile to the next tile. You want to do tile hopping, and when you are done you have processed all the tiles. Okay, now this depends very much on the layout obviously, and there are ways to do that. Hierholzer has found algorithm that actually allows to handle this problem in linear time based on Euler graphs, and that leads to very interesting results. So if you have an aligned tiling, then you see that one A node corresponds to exactly one B node. So you actually get separate, isolated subgraphs, and that tells you you can do that in parallel, independently. But not always life is such nice. In the other situation, bottom right, we have non-coherent tilings, and then actually we need to find a path, which is not so easy, and sometimes we need to introduce auxiliary paths. That is, we indeed need to load duplicate tiles, but actually the Herholz criterion indicates us that this is the minimal number of nodes we need to load. So we find a minimal path over this graph, and so it can be proven that this array join algorithm actually is optimal in the number of tile loads. Okay, and then whenever it comes to large data centers that are used to handle parallelism, of course they are so interested in, and how do you do parallelization and distributed processing? Well, the good thing is we know the language, so we know the semantics, and if we get such a query like you see in the gray box, then our node A can say, I see, I can evaluate the yellow part because I have dataset A. Not so, however, the orange part, because I don't have the data. But I know a friend in the cloud that does have dataset B, and so I actually cut out a subquery and send it over to node B. Node B actually doesn't need to differentiate. It doesn't know that this is part of a larger query. It computes the result duly and sends back the result. So this is how we do cloud parallelization. And you can see that as compared to Hadoop style parallelization, we are much more flexible. The nodes can do completely different things, and so we achieve a higher degree of parallelization. That we have driven so far as to go over 1,000 cloud nodes in Amazon, and that works nicely. This encouraged us to say, wait a moment, we also can go this way to another data center and do federation. So the blue subquery actually would be sent to the blue house, to the blue data center, processed there, and only the result comes back. And this is how we do federation of data centers today. And actually we can go up to moving targets. We have one project with the European Space Agency where we have installed rasterman on board a satellite, so that you can send queries up to the satellite and they are computed on the images right as they are taken by the satellite. This federation principle I want to show you briefly in a live scenario. So we jump over to a demonstration where we use another language which is not SQL but which is the OGC WCPS, which is Web Coverage Processing Service. It's actually GeoDataCubes. So without going into the details of that query, what it does, we send it to Fengjia University in Taiwan, and now we see the path of the query as it walks. It goes to Fengjia and they find out, oops, we can't solve it alone because we are lacking some data. So they need to send a subquery to a server in Germany, and then we get back a result, which in this case is the vegetation forecast for northwestern of Taiwan. We actually could send the same thing to the German data center. Okay, wait, that doesn't work. So let's stop here. Hanging demo is always something nice in a live presentation. I love that. So actually the federation becomes one big pool of data where you can send the query to anywhere, and the nodes will find out how to best evaluate that. Currently we do it according to very simple rules. Number one, ship code to where the data is, so process close to the data. Rule number two, minimize transport between the nodes. But there is an ongoing advanced PhD work that actually generalizes that, so that we can consider much more advanced rules there. Okay, so the overall architecture of the rasterman system specifically now is we have the EarthServer processes in the center. They are the workhorses that are parallelized without a single point of failure. The pixels can be stored in a relational database. This is how we started early on. So works nice, for example, in PostgreSQL, but we also did it in Oracle, in IBM DB2, etc. But then people said, we don't want to have an extra component here. can't we do without? So we implemented our own storage manager directly on the file system, so POSIX file system or S3 containers, and that allows us to conveniently manage our own tile store. It's about 2 times faster than PostgreSQL, and all was nice until the big data center said no. Forget about copying data into another place. We are talking about petabytes of data, and we just cannot copy that. So we had to learn something that is a little bit scary, working on data that are not entirely under our control. Today, you just tell us the conventions of your archive, and then we register data, and then query processing goes on as usual. So this is the Rasterman server system. It is domain independent. We have a geosemantics layer on top of that, a business logic that knows about the semantics of space and time, so it also knows about regular and irregular grids, and that is offered via OGC, Open Geospatial Consortium compliant interfaces as web services. So that is in a nutshell the resulting architecture. What we also got presented with is security. Now, role-based security is an old thing, it's well known. It just turned out it's not enough. Here's an example. The European Center for Medium-Range Weather Forecast maintains long climate time series, hundreds of petabytes. These are free to access, except for the most recent 2 weeks, for which you have to pay. So this policy actually requires that our access control is more fine-grained. Data cubes are just too big as a unit. We must go inside, and so we had to find a way. What we in the end did is, in the first step, implemented role-based access control, so we have users and roles and privileges as always, and then we combine that with database triggers. A trigger is again like the usual definition, just in one place it gets particular, and that is when we talk about what is accessed actually. So in the condition expression, in the when part of these ECA rules, it gets specific. Because now we can actually indicate areas inside an array that should be protected. That can be via a bounding box, like in this case here with ECMWF, but it also can be a polygon or a mask or some computed criterion, whatever. Essentially, we can protect down to the level of single pixels. So you see such a trigger here with a forbidden area, and whenever in my coverage this area indicated gets accessed, that is at least one cell gets accessed, that is what the sum cells operator does, then actually an exception is thrown and the system says, dear user, unfortunately you have insufficient access rights. This allows us to protect, and then actually at times we need to exempt people. So some particularly powerful users like administrators, they should be able to access, of course, despite this trigger. So we extended the grant statement to allow exemptions, and user U, for example, could access the forbidden area without any problem because this user is exempt from that trigger. So that is our approach in a nutshell to security handling of arrays as a big data problem of another kind. Okay, so much about the technology. Time flies. Let's go into applications. So one thing that we have done at some time back already is human brain imaging. If you put a human being into a scanner and ask it to do a job like what is the square root of 82, you can get some brain activities, and after a lot of processing from those PET or fMRI or other modalities, you get so-called activation maps. These activation maps give you the areas which are particularly active currently, and in this image here you can see, for example, 4 threads that are particularly active. So you could ask, are these always activated together? And by the way, to what brain organs do they belong? So we need to look into a brain atlas where we find, for example, the definition of hippocampus, and then we can do statistics. So this example query here, a parasagittal view of all scans containing critical hippocampus activations, will simply translate into a statistics query that searches over all the brain images to find those ones that match the criterion. Okay, another area of life sciences was gene expression analysis. The example here is with Drosophila melanogaster, or commonly known as fruit fly, where actually we want to study the evolution of embryos, and we want to see how the genes get activated and deactivated. So we take the embryos, we slice them, and then under some specific light conditions they get illuminated, and we can see parts of the body that are active and others non-active. We can combine 3 of those into an RGB image, and then we have a nice image that is already nicer than the hand-drawn images that had been done earlier. But actually, in an array database, we now can see such patterns as some 4-dimensional cube, where the volume of the embryo actually evolves over time, and then we can do 4-dimensional processing and queries on that, which makes it massively easier to handle. Let's go bigger, cosmological simulations. So dark matter and baryonic matter get simulated in ways that are way too complex for me as a computer scientist to understand, and then some mighty complex simulation gets out results which are 3D or 4D cutouts from the universe. Below you see a tool that's called AstroMD, that also has been done some time back already, as you can see, together with colleagues from Cineca in Italy. And we get data cubes where we want to find out where how do the galaxy superclusters behave, for example, or, as is important today, what about the seemingly empty space in between. Getting back closer to Earth, here's a service, planetserver.eu, that actually has information about Mars, Moon and Vesta, and here you can do analytics and can study hyperspectral satellite images with hundreds of channels. ECMWF, you see we are getting closer to Earth again. River discharge is one of the things they did do in a spatio-temporal way. Daily hydro estimator, so how much water is in the atmosphere, stuff that has been done here. Then actually you can do simply stuff like visualization. So such a query can generate a 4-channel image with red, green, blue. That is what we understand. And in the alpha channel we actually put elevation information. And WebGL client in the browser can generate a 3-dimensional terrain draping, a rendering, which you then can turn and enlarge so you can navigate it in your browser. So this is a case where actually array queries can feed visualization. Okay, so let's summarize. This was a quick overview on things that we have done over time, and as I said, we always were aware that arrays never come standalone. So we need to think about embedding. So in these 4 fundamental data categories that we spotted, and if you know about a 5th one, please let me know. I'm glad to enter into such a discussion. Then we would need to combine arrays with SQL. I showed you that occasionally, but also with XML, for example, when it comes to hierarchy embedding, or what about Sparkle when we go into semantic web world. There are obviously several ways of doing that. The one with SQL actually meantime became part of the ISO SQL standard. It goes by MDA for multi-dimensional arrays, and you can see in the yellow boxes that such an attribute like scene suddenly can become an MD array, a multi-dimensional array, and has an extent. And in the select query you can process that and get back, say, images, but you can use it also in the where clause for filtering. So since 2019 this is an official component of SQL. XML integration we have done in another context, in the Open Geospatial Consortium, because their geometadata typically come in XML, so it makes sense to link that seamlessly between data and metadata. And of course XQuery is the basis for that, flower expressions. And so you see something like a for loop where we go through the coverages. We have some criterion, NIR greater than 127. We combine it with a metadata criterion, and then we go into the processing of it, and we return some TIFF images which result from this processing. So this actually shows you in a completely different language and model embedding how such a combination could look as well. By the way, you also could do what we call a reverse lookup. You don't search from metadata to data, but you go the other way. You search for data properties, like find where infrared is greater than red, and then you return the metadata, like the identifier and its boundary. That has been implemented by Athena Research Lab in Greece, based on a federation of the EXIST XML database system and rasterman. There was also experiments with RDF based on Amos 2 from Uppsala University. They have a tool called SciSparkle, and that has been combined with array queries, and in that flavor you see that we have the typical RDF and Sparkle predicates, and then there is a function NDVI for the vegetation index again, which contains the formula that we have seen a couple of times now. So basically it can be done in all these different languages. Embeddings are possible, but I'm sure that other researchers would come up with other ideas, so this is an interesting field to pursue further. With that, let me conclude. I tried to make the point that array analytics is something essential also for databases. Why? Hey, it's about data. It's about big data. So it's definitely something where we should have a say. We didn't have a say in the past, and therefore silo solutions, homegrown solutions, which have several severe disadvantages, have prevailed. We can contribute something that can do better. Actually, this is used all over the place in science, engineering, business, fintech, and so on, as sensors, image data, simulation data, statistics data, etc. So generally speaking, array DBMSs must support n-dimensional tensors and linear algebra operations on that. We have seen that in the rasterman system. We have accomplished that to some extent, but there is still quite some mileage to go, a long way to go. But generally speaking, from a database system perspective, we can contribute what always is the advantage of a database system. We can contribute the flexibility of any query anytime. We can contribute scalability options. We can contribute optimization, and in particular information integration. So if you look, for example, at ISO SQLIMDA, you suddenly do queries that don't differentiate between data and metadata. You just get a seamless information plane. There are many, and I mean many, exciting research questions, and there is quite some active research going on in many groups over the planet. So it's about conceptual considerations on the expressiveness of languages, down to optimization techniques where there is a wide open field available, and also other scalability options. I cannot go into all of these. I have stretched your patience long enough. I showed you that based on the insights and the implementation of rasterman, which, without us knowing it, has pioneered array database systems. It is in industrial use on petabytes of operational databases, has been parallelized over more than 1,000 nodes. So the concept definitely has been proven, and thereby it also has become the blueprint for several standards on Datacubes. So we hope that we have helped arrays to come from underdog level to first-class citizens in conceptual modeling and in technology support, but we also humbly respect that by far we haven't been the first ones to think about arrays. Maybe the first one who has some documented research on that was Salvador Dalí, where you see his thinking about array services in the picture here. And with that, let me thank you for bearing with me all that time. If you want to visit us, here are some URLs that lead you to our outcomes, and maybe you just want to contact me and drop me a note so that we get into conversation. So thank you for now, and let me stop here. Have a good SSDBM.